Thanks. My name is Monika Schleier-Smith. I'm a physics professor at Stanford University and a researcher in quantum information science. I'm here today to say a little bit about what quantum information science is. And to start with, I thought I'd take a step back and actually say, how is information encoded classically on your computer, right? So the fundamental unit of information is a bit. That could be a 0 or a 1. And on your hard drive, for example, the way that we store a bit is in the magnetization of some region of your hard drive. If the north pole of that magnet points up, that would be a 1. If it points down, that's a 0. That region of your hard drive consists of many millions of atoms. But if you shrink that down to the level of a single atom or a single particle, such as an electron, then describing its behavior requires the laws of quantum mechanics. And we're left with that single particle being something that could be used to represent a quantum bit or a qubit. So a quantum bit could also be in a 0 state or a 1 state, which we could represent. We often visualize it as an arrow. That's sort of that magnetization that could point down or up. But it could also point somewhere in between. So I've drawn here these kind of arrows on spheres representing the states of these individual qubits. And the neat thing in quantum mechanics is that actually, rather surprisingly, when you measure the state of a qubit, it might be a 0, it might be a 1. But if that arrow is pointing somewhere in between, that actually means there's some randomness in the measurement outcome. So that if you were to prepare that same state many times, it would be almost, measuring its state would be almost like performing a coin toss. Sometimes you would find 0, sometimes you would find 1. So one of the kind of remarkable features of quantum mechanics is that it predicts probabilities, but there can be randomness in the behavior of the physical system. But it's not just any randomness, it's not just any coin toss. Even more remarkably, let me actually give you an example of something that can happen in quantum mechanics. So we could have a situation where Alice has a quantum bit and Bob has a quantum bit. I'll think of it as Alice and Bob are tossing coins. And Alice might be in my lab at Stanford, and Bob, let's say, is in Washington, D.C. And each of them performs a measurement on a sequence of quantum bits. And if Alice alone looks at those measurement outcomes, they will look completely random. So sometimes she'll see heads, sometimes she'll see tails. And if Bob looks at his measurement outcomes, they'll also look completely random. But when Alice and Bob compare notes, they could find that actually the outcomes are always correlated. Every time Alice has heads, Bob gets tails, and every time Alice sees tails, Bob sees heads. Now, this would never happen if we were literally just tossing coins in different rooms across the country. But in quantum mechanics, this can happen, and that tells us that there's information that Alice doesn't have. Her measurement outcomes look random. Bob doesn't have the information, but it's somehow shared between them and distributed non-locally across the country. So this fact that information can be stored not just in individual particles, but in correlations, those correlations are known as entanglement. And this phenomenon of entanglement has some remarkable implications. So for one thing, it means that if I have just 2 qubits, in order to sort of keep track of the state of my quantum system, if I wanted to describe the state of the system, I need at least kind of 4 numbers that tell me something about the probabilities of getting these different measurement outcomes, which aren't all equal. So there are 4 possible outcomes if I have 2 qubits, but if I had 3 qubits, there would be 8 possible outcomes. If I had 4 qubits, there would be 16 possible outcomes. And as I keep increasing the number of qubits, you very rapidly get to the point where, let's say you have 40 qubits, there are a trillion possible outcomes that you need to keep track of. If you get to just order, let's say something like 70 qubits, you'll never be able to fit a description of that system onto even the world's largest supercomputer. And that's that exponential growth of complexity of the quantum system that you heard about in the previous introduction. So that entanglement and that resulting complexity has a number of potential technological implications for really harnessing these remarkable properties of quantum mechanics. One is in the area of computation. Because even just a system of some tens of quantum bits can never be described on the world's largest supercomputer, that already starts to indicate that it could have some power to do computations that aren't possible with our current classical technology. And those could be computations that are relevant for solving, let's say, chemistry problems that are important for discovering better medications, material science problems that could help discover better superconductors, as was mentioned in the previous talk, optimization problems that can help with societal problems like supply chain logistics. So these are all things that quantum computers are hoped to be able to help us tackle, taking advantage of that power that classical computers don't have. A second direction where quantum technology promises to have really revolutionary implications is in precision measurement. So remember, I talked early on about that sort of randomness, that coin toss that constitutes a quantum measurement. And that randomness, it's almost like the statistical uncertainty in a poll. The more people you poll, the better you can trust the result. And similarly, sort of if you want to do a very precise measurement with a small number of particles, the best you can do is going to be limited by these quantum fluctuations, that statistical uncertainty. That means that if you want to, let's say, optimize the combination of the precision and the spatial resolution and the sensitivity of, let's say, medical imaging technology that relies on precisely measuring magnetic fields, you need to really understand the laws of quantum mechanics. And by harnessing that feature of entanglement, one can actually have those correlations conspire to reduce the statistical fluctuations in the measurement outcome and give you better magnetic field measurements for medical imaging, better measurements of acceleration or time, which are essential for applications in navigation, such as GPS. And so harnessing really the full potential of quantum mechanics will have transformative implications in the area of sensing. And lastly, we talked about the fact that Alice and Bob can have some information that is somehow not in the possession of either one, but shared between them and distributed non-locally across that long distance, across the country. And it turns out that that can be a resource for having fundamentally secure telecommunications where Alice and Bob can share some information that nobody else can know. And that is another sort of crucial application, quantum communications, where we envision impact for future quantum technologies. So with that, I've given you kind of an overview of what quantum information is and some of the exciting applications. And over the course of this program, I hope you'll enjoy also hearing the perspectives of other researchers and what particularly excites them most about quantum mechanics. So with that, thank you, and I'll pass it on to our next speaker.